All right, we're back for round 2. This video is going to cover topics 7.3 and 7.4. You're going to need to have a calculator handy for when we get to 7.4. Pretty much the rest of this unit is all calculation based. A reference sheet would also be beneficial. Okay, so topic 7.3 is about the reaction quotient and equilibrium constant. And so you're going to be able to represent a reaction quotient, QC or QP, for a reversible reaction and the corresponding equilibrium expressions. I will explain. I'm just going to jump into the content. That stuff's all background and reference sheet that I'm going to go over. Okay, so here's the idea. There's this thing called the law of mass action, where we can mathematically depict a process showing the rate of a chemical reaction directly proportional to the product of the activities or concentrations of reactants. What you're going to see is the ratio of products to reactants is constant. Okay, so we're going to look at something called an equilibrium constant. Here's the idea. It's based off of the rate law, which we did in kinetics. Okay, so if I'm dealing with this process that is reversible, right? If I'm just looking at the forward reaction, so I'm reading this from left to right, the rate law could be written for this forward process. Rate equals the rate constant for the forward process times the concentration of N2O4 raised to the first power, assuming this is like an elementary step, right? We can use stoichiometry. So the rate law for the reverse reaction, if I flip it around, would be rate equals K of the reverse reaction times the concentration of NO2 squared because of the stoichiometry. Now, if I put those two things and set them equal to each other, because at equilibrium, the rate of the forward reaction is equal to the rate of reverse reaction. So the rate law for the forward reaction would be equal to the rate law for the reverse reaction. Now, if I want to isolate the concentrations on the same side and the rate constants on the same side, I can divide by each and make it into this, what's called a mass action expression, where I have the forward over the reverse rate constants on the left, and then I have, you can see it better this way. If I bring the N2O4 over here, then I have NO2 squared over N2O4. I will explain, this is a lot simpler than what it looks. Okay, so here's the idea. This reaction quotient expression, or Q, okay, is also known as the mass action expression. It can be written for a chemical system at any point in time, beginning, middle, equilibrium, whatever. It's a way to express given concentrations of reactants and products. Basically, you write the expression and then you substitute in the numbers that you are given. If you see a Q with a subscript of C, that is referring to concentrations in molarity. So this is the way that it is written. So here's my reaction, okay? Coefficient of A for substance A, coefficient of B for substance B at equilibrium, okay? Coefficient of C for substance C, coefficient of D for substance D. The reaction quotient, Q, is equal to, why is this like this? It should be this, should be this, sorry. Should be this should be this, okay? It's equal to the concentration of C raised to its coefficient power times the concentration of D raised to its coefficient power over A and B each raised to their coefficients. So it is products over reactants raised to whatever their coefficients are in the balanced equation. Here it is again. Okay, so what are all these pieces? A, B, C, and D, capital A, B, C, and D are all the substances that are going through the reaction. Square brackets are referring to molarities, right, concentrations. A, B, C, and D in lowercase are the coefficients. I will review this with you. You will omit solids and liquids. So if you see a little S after something, or if you see a little L, it does not get included in the expression. Only gases and solutions are included in a mass action expression. And that Q reaction quotient will not have any units, because the units gets way too complicated once you start like raising it to different powers and stuff. There's no unit. Rate constant has a unit, Q does not. So again, what do we include? We include any gases in the reaction. We include any solutions or aqueous in the reaction. We do not include solids or liquids. Here is an example. Write the mass action expression for this following process. So the first thing I'm going to do is make note of the phases because I need to know whether to include it or not. Q is equal to, it's products over reactants raised to whatever their coefficient is. So concentration of tin positive 4, that would be raised to the first power because its coefficient is 1, times the concentration of iron positive 2 raised to the second power. There's that. There's my products, my reactants, tin positive 2, so it's obviously a redox reaction, times the concentration of iron positive 3 raised to the second power. That's all you have to do to write this expression. It's products over reactants. Their concentrations will be raised to whatever their exponent or whatever their coefficients are. Now, if your substances are gases that you're working with, you may be asked to write an expression in terms of pressure, okay? So it would say QP. Now, the deal with that is, you can ignore this. Instead of brackets, which brackets only denote molarity, okay? You would put pressures in those spots instead, pressure values that they would give you, okay? You're not guessing these numbers or anything. They're giving you the numbers. Or you might just have to write the expression. But the format's exactly the same. It's just pressures instead of molarities. Okay, so let's just look at this example. For this reaction, the pressures of sulfur dioxide gas, oxygen gas, and sulfur trioxide gas are given. Let's write the mass action expression and then just substitute in the values. We're not even going to solve it. We're just going to write it. Okay, so since we're looking for pressures, we're given pressures here, we're going to write QP equals. Now it's got to be products over reactants, and each is going to be raised to whatever their coefficient is. So it's going to be the pressure of SO3 squared, that's my only product, divided by the pressure of SO2 squared, I don't know why I used parentheses there, times the pressure of oxygen, and that would be raised to the first power, okay? Products over reactants. If I just substitute in the values that I'm given, sulfur trioxide, 0.98 squared, over sulfur dioxide 0.66 squared times 0.51, and you don't have to write to the first, but I am just for reinforcement. That's all you have to do. So here is another one. So I'm going to have the video pause and have you write this one. Okay, so now what you need to be careful of with this, dun dun dun, boo, solids are never included. Okay, so it simplifies it, right? The pressure of CO, product, raised to the second power, divided by the pressure of CO2 raised to the first power. Okay, solids and liquids are never included. It doesn't matter if it's a concentration-based one or a pressure-based one. Solids and liquids are never included, just aqueous or gases. Now, taking this a step further, the equilibrium constant expression, which is denoted by a capital K, right? Lowercase k is a rate constant, capital K is an equilibrium constant. Thanks for using the same thing. It's also potassium, but you know. It's written the exact same way as a Q expression. But when you denote an expression as being equal to K, that is exclusively for systems at equilibrium. Okay, so we use K when we know we're dealing with a system at equilibrium. And you can have a concentration-based equilibrium constant, or you could have a pressure-based equilibrium constant, just like we had Q. It could be concentration-based or pressure-based. Same deal with including things that are gases or solutions, excluding things that are solids or liquids. This is on your reference sheet. It gives you both versions and how to write it and where it would come from in an equation. And it also tells you what it means. Okay? It's given to you on the reference sheet. So cute. Now, when you're dealing with the concentration-based equilibrium constant and a pressure-based equilibrium constant, their values might not be, their numerical values might not be equal to one another. There is a conversion to get from one to the other, but you do not need to know it. What you do need to know is that the concentration-based equilibrium constant and the pressure-based equilibrium constant will be equal to each other if the total number of moles of product of gases is equal to the total number of moles of gaseous reactants. Those two things will be equal. But there is a conversion. You don't have to know the conversion. I forget it because tiny lizard brain, remember? All right, so here's an example. And just to show you how the format would be different for a concentration-based or pressure-based equilibrium expression, we'll write this out. They're formatted the same way. So here's pressure-based would be the pressure of NH3 squared divided by the pressure of nitrogen raised to the first power times the pressure of hydrogen cubed. If we're doing this as concentrations, it would be the molarity of NH3 squared divided by the molarity of nitrogen to the first times the molarity of hydrogen cubed. So you can see the placement of the substances is the same. The exponents that you're going to be using are the same. But if they ask for a Kp and you throw brackets in, it will be wrong. It's on the reference sheet. It shows you how to format a pressure-based one versus a concentration-based one. Now, what the heck is the difference? Like, why did you show us, crazy lady, how to do a Q and also a K? There is a difference. Q means that one of two things. We either know for sure that our system isn't at equilibrium, like currently, or we're not sure and we got to calculate and test it out mathematically, which I'll explain later. Okay, so saying Q means we don't know if this is at equilibrium or not. Saying K means we know this is at equilibrium. The setup is exactly the same. The math will be exactly the same. But if you're given a reaction with some values and they don't tell you if it's at equilibrium or not, you have to write Q, not K. I know it's nitpicky. Last couple things here in this little section. If you're dealing with a system that you would call a homogeneous equilibrium, that means that everything in the system is in the same phase. Okay, cool? I'm not gonna go over writing those, but that's it. If you're dealing with a heterogeneous equilibrium, you do not have the same phase throughout. Okay, so for this particular one, if we were to write the equilibrium expression, if we'll do a KC here, solids aren't included. So it would just be the concentration of O2 cubed. That's the product, and there's no denominator, right? Because there's no reactant in the gas phase or aqueous. For the second equation, it would just be those two that are included. There would also be, I love when it makes automatic ovals. There'd be no denominator in that one also. Okay, so that takes you through how to write a mass action expression. This next section, I forgot these guys. Look at these guys. This dude and his brother-in-law developed it. And look, they're really, really cool. They really like to party. I'm sorry, I'll go now. Just kidding. We're gonna do the next one. Now we're just gonna plug numbers in and solve, okay? That's all this little section is taking the written expression, plugging in numbers, and actually pushing the buttons on our calculators like good little robots. Okay? Okay. So here, determine the value of Kp given the following equilibrium pressures at a certain temperature. So it's telling us that it's at equilibrium. So we know we can use the letter K. All right? So first we have to write the expression. Kp equals the pressure of NH3 squared divided by the pressure of nitrogen to the first times the pressure of hydrogen cubed. Now we put in our numbers. 2.9 times 10 to the negative second. I'm just going to convert those because those exponents are tiny enough that I don't have to like really go nuts with it. Squared. 0.89, that's to the first, and 0.0029, that is cubed. Okay, so now I plug my numbers in, 0.029 squared, so calculator is our best friend. 0.89 times, I like to use the parentheses here, 0.0029, and then in calculator math, the math button, number 3 gives you a cube, if you're not familiar, and that is equal to this. Okay, now what does that mean? We'll get into what that means, but what I want to show you is the value that you get for K or Q can vary like super duper crazy values. Like you could get like 10 to the 35th power or like 10 to the negative 28th power. Like those are okay answers. So you can't ever be like, oh, should it be within this range? Oh no, it just depends on the numbers you're working with. Okay, so just careful with your math. All right, how about this one? This one gives us the Kp. Find the pressure of chlorine if PCl5 pressure is 0.075 and PCl3 is 0.463. So we're just solving for something other than the K. But we're going to write the Kp expression, because we're good little soldiers. The pressure of PCl3, that's to the first, times the pressure of Cl2, and that's also to the first, divided by my reaction. Oh, it's also raised to the first. How cute. Okay, so now we substitute in. Kp is 1. See, look at that. Cute little number, right? It's not 38,000. It could be, there's so many different values you can get for these. PCl3 is 0.6463. PCl2 is what we're solving for. And PCl5 is 0.875. Okay, so I'm just going to cross multiply because I'm crazy like that. 1.05 times 0.875 is equal to 0.91875. That's equal to 0.463x. Divide by 0.463 on both sides. X is equal to 0.91875. Oops. Divided by 0.463. So that is 1.98. Now we can give that a unit because it's asking us to find the pressure. So that would be atmospheres. Okay, so it's just algebra, things to remember about K. You want to make sure you capitalize it. K is a constant as long as the temperature is constant. And we'll talk about what happens if you alter the temperature later on. So there's only one value for K at a given temperature. And that's it for that part of the show. That was just learning how to substitute in your values. The next lesson we'll talk about what does that value mean, like in terms of its magnitude, and also how can we manipulate the number. I know you're very excited.